Hello, this is Murray Einerson, a hydrogeologist with Haley and Aldridge in Oakland, California. I lead the CSM service at H&A, and CSM stands for Contaminated Site Management. And I'm here with Peter Bennett, who's the leader of our remediation practice at Haley and Aldridge, or one of the leaders. And Pete, you've been involved with several research projects in your career, including some funded by CERTUP and ESTCP. So a question that I hear a lot that I'm going to ask you is, with all of this exciting innovation and new approaches being developed in these applied research projects, are they practical? Like, can they be practically applied at real sites?
Yes, thanks, Murray. I absolutely, I believe these programs are important and are ultimately going to solve some of our largest remediation problems at groundwater sites.
And so, why do you say that? Can you give us a couple of examples?
Yes, large dilute plumes comprise a large portion of complex sites, and they're often the most expensive to deal with, and tend to have larger liabilities associated with them. And typically, for large dilute plumes, groundwater extraction and treatment is the go-to, and has been for decades the go-to remedy. And that invariably involves a treatment plant above ground with a footprint on property somewhere, and property is becoming harder to find as industrial areas are becoming developed and turned into communities. And we have to wonder in the future, is it really going to be realistic to have to install treatment plants and multi-well networks and trenches in city streets? At some point, it's already starting to become more difficult. So we need solutions for that. We need solutions for these plumes, and I think the applied research is pointing us in a direction where we can, we have a line of sight to some of these solutions.
Yeah. So, can you give an example of one of those that you could share with us?
Sure. I guess in my view, I think that the co-metabolic processes really have an expanded role in the groundwater remediation practice. That can be for both ex situ and in situ treatment methods, but I'd like to focus on in situ, and I think that we should, in order to decrease footprint and things like that, we should be thinking more about in situ processes. The fact that co-metabolic processes can target the low concentrations that metabolic processes often can't get to, I think that is, our cleanup goals are often too low, difficult to treat with metabolic processes. So the co-metabolic processes allow you to get to those lower concentrations. They typically have less impact on water quality. You're not having to add as much substrate to groundwater, and have shown to be effective for emerging contaminants, like, for example, 1,4-dioxane, the aerobic co-metabolic degradation of 1,4-dioxane. So I think that we're starting to see these technologies move from applied research to field studies, and now we're seeing them being applied at groundwater sites. So I really think that's a shining example of how applied research has translated to solutions for groundwater sites.
So, Pete, when I think of and hear of co-metabolic processes, I think of simultaneous additions of electron donors and electron acceptors. It sounds complicated. Is it complicated, or how can that be implemented in a practical way?
Well, it can. Every site certainly has its complications, but I think what we're with certain innovations on the delivery side of things, we can look at least decreasing the footprint of these systems, decreasing O&M burden, and getting to a system that is more effective and less burdensome. So one of the examples of that is our ESTCP project, ER 155168, which our colleague Jacob Chu is principal investigator on. The idea here is that we have groundwater circulation wells that are installed at the same location, but on an angle angled 180 degrees from one another. So you can see on the screen here, we have an extraction well that's going off at a 45-degree angle to a deep water table, say more than 100 feet deep. And we have an injection well that is opposite the extraction well. They both are in the same below grade precast concrete vault. So you can pump water from the extraction well and transmit it right to the injection well without the need for conveyance piping between the two and controls and all of that, conduit for controls. So that allows for these sort of a modular design for groundwater circulation systems where you can have a number of these. I think what the future of this would be to have a number of installations like this along the axis of a large dilute plume. And substrates are gaseous amendments like oxygen and propane can be added in the same below grade vault, and it's pulsed operation to promote the degradation processes, ultimately to transition to M&A or get get below cleanup goals and closure of the plume. So that's something that one example I think where we need to be thinking about how these processes, these really effective processes for treatment, can be applied, but also how can they be applied in a way that's pragmatic and that has certainly a less footprint in the areas where they're installed.
All right, Pete, I think we're running out of time here now, but I really appreciate your thoughts, in particular on transitioning some of these innovations from academic research to practical implementation at real sites. So I'll look forward to our next discussion. Thanks for taking the time today. Take care.
Thanks, Mark.